Hello everybody. In this video, we are going to solve the question 19 and 30 in algebra section in week 8 of the Maths 1251 at University of New South Wales. Okay, B is a fixed vector. That's a vector, just a fixed vector. Sorry. It is known, we don't know what it is, but we are taking a general position, a fixed vector. And T is a map defined from R3 to R3 and given by the rule that we will multiply every vector with the cross product with this fixed vector B, whatever it is. And we would like to prove that T is a linear map, and we would like to find out the matrix form of it. Okay, that's the question. Now, first we need to understand what's going on. So let's have a look. Any B, let's say B is B1, B2, B3, and X is any vector, X1, X2, X3, a general position this vector, and have a look this cross product. Now we have IJK. I don't know how you're looking at the cross products, but this is by the definition. I'm solving it by the definition. There exists a quick way of doing it as well. You're taking the two vectors one by one and doing it with your eyes. Whatever it works for you, as long as you're doing the correct way of calculating it, is perfectly fine. So this is basically determinant of this matrix. So we have IJK basically representing the unit vectors in the three-dimensional space, E1, E2, E3. I is E1, J is E2, and K is E3. Okay, since this is a determinant, calculations of the determinant, and we are opening up this determinant, computing this determinant with respect to the opening up the formula with the first line. And the first line, we have the position I, so this is in the first position, first row, first column. So this is -1 to the square, that is positive. And the entry here I, and then we are removing this row and this column, and we have a determinant of this 2 by 2 minor, which is B2, B3, X2, X3. And for this, the second one is J. J is in the first row, second column. So this is why we have the -1, because that's -1 to the 1 plus 2. That will be the -1 to the cube, that is -1. So we have -1, and this -1 is important. Don't fail to do so. That's really important. Not everything is plus in this cross product. You know the cross product, but just I'm extra vigilant. And it means that we are removing this row with this column and calculating the determinant of this minor, which is B1, B3, X1, X3, which is this guy. And the entry is just J. So K is in the first row, third column. That will give you the -1 to the power 4. That will be plus. So this is why you have plus. The entry is K. And then removing this row with this column, you have this minor, which is B1, B2, X1, X3, which is this one. So this is basically the definition of a determinant. So this is a determinant of this matrix. So this is what we are doing. So the determinant of this minus will be this times this, minus this times this, and similar to for the others. Then we have this vector. We can write this vector as IJK position. So this is the coordinate vector of this vector. This vector is written as a linear combination of IJK, and we can rewrite this as a coordinate vector with this way. And now, and X1, X2, X3 is unknown, right? And I can rewrite this as a matrix multiplication, because if I multiply this row with this column, I will get this. So but this what I'm doing here, Basically, there's no coefficient of x1, so this is 0, and the coefficient of x2 is b3, and the coefficient of x3 is b2. And this way, I'm constructing this row, and which will give me the exactly this entry when I multiply this times this, right? As a matrix multiplication, as a dot product of rows and columns. So this times this will be that. And this times this will be a coefficient of x1 is b3. So I have b3. There's no coefficient of x2. Coefficient of x3 is minus b1, which is this guy. Coefficient of x1 is minus b2. That's 1. Coefficient of x2 is b1, which is this one. There's no coefficient of x3, so that's 0. When I multiply this times this, I will get this. So this is the matrix form for this linear transformation A, and I can write Tx as B cross product as A times X, as we've done here. So once you got this far, it is obvious that A is a linear transformation because you already express it as a linear, as a matrix form. Is if you can do it, it is definitely a linear map. It is obvious because this way. If you have lambda mu, real number scalars, and x and y, any vectors, so transformation lambda x linear combination of x, y with lambda mu exactly means that the matrix multiplied by this vector, but this vector will be a times lambda x, a times mu times ay, distribution law of the matrix multiplication. So via the matrix multiplication, you will immediately get linearity for this map because matrix multiplications are linear. Or you can do that with respect to you can prove that T is linear by using the definition of this map. And the definition of this map was the cross product. If you use that, you take lambda mu are real numbers. So they are your scalars, and x, y's are any vectors, and linear combinations, applying this as input, and then you have applying T. Now you apply the definition of T means that this vector is a cross product by B. That's a cross product by B. But now then you need to use the cross product properties, and the cross product properties gives you that there's a distribution law, and there exists a scalar can be moved in and out in a cross product. So it will give you this expression, which will give you the lambda Tx mu Ty. That gives you the T is linear. Okay, that's question 19. Question 30 is also related with this calculation. In this case, we choose, in the question 30, there exists a B, a vector, a fixed vector given. That's 1, 2, 3. And in that case, let's see what will happen. And second part, prove that T is linear. And the second part of this question, dimension of the kernel T. So from the question 19 we've just solved, we know that matrix form of this transformation is given by this formula. And I'm just using directly the calculations we've done in the question 19. If B is equal to 1, 2, 3, I'm just placing those ones into the right places here, right? That's B1 is -1, B3 is 3, B2 is 2. So that's the matrix form for this linear transformation. Since, as I explained just a minute ago, A is a linear transformation. We've just proved that. Now, what is the dimension of the kernel T? So kernel T and the kernel of the linear transformation is equal to the kernel of the matrix form of this linear transformation. So we know the matrix form. If you apply the reduced row, if you apply the row operations, you will have a reduced row echelon form of this kind. You will get this. So the last row tells you that x3 or actually there is no leading coefficient. This is a leading coefficient x1, this is the leading coefficient of x2, leading coefficient x3 is not there. So the last row tells you that x3 is a free variable. If you say x3 is equal to lambda, from the first row, we have x1 is equal to 1 over 3 x3, right? x1 plus 1 minus 1 over 3, x3 is equal to 0. So you take that one on the other side, you get x1, 1 over 3 x3. From the second row, we have x2 is equal to 2 over 3 x3. That is basically when you put x3 is equal to lambda, x1 is 1 over 3 lambda, x2 2 over 3 lambda, and x3 lambda. So the vector is spanned by 1 over 3, 2 over 3, 1. So the kernel of T, or the kernel of A, is the lambda times of this vector. Lambda runs through the all real number, but this is a definition of a spanning set. That means that that is a span of this vector. Okay, so you have found one vector which is spanning the whole kernel of A, or kernel of T. So the dimension of the kernel space is just 1. So that's, we call kernel a nullity as well. That's the dimension of a kernel is another name, which is a nullity. So that's one. That's all for this section, for this video today. Thank you very much for your listening. I hope it is helpful for everyone.